Hi everybody, I'm Razvi. Welcome to another video from the binary exploitation series. In this video, we are going to learn what return-oriented programming is, also known as ROP. We are going to see the most important aspects about this exploitation technique. That is, what it is, how does it work, and how we can abuse it to exploit some binaries, to pwn some binaries. We will first discuss a bit of theory that is needed in order to understand the vulnerability, and then we will jump right into practice. In this case, we will be exploiting the split challenge from the ROPEmporium website, which I will later show you. As always, I will explain the key concepts about this exploitation technique, and in case you want to further your knowledge, there are references galore on the internet. I have here just a few examples. For example, return-oriented programming entry on the Wikipedia. We have ROPEmporium website that contains the challenge we are about to exploit. We have return-oriented programming from Fuzzy Security. Another information security lab about return-oriented programming. ROP chaining from iRead team. Introduction to return-oriented programming from Code Arcana, return-oriented programming from CTF101, and we have also the entry from Rapid7 about return-oriented programming. All these references will definitely help you understand the exploitation technique itself. Of course, I will link them in the description of the video. But first things first, what is return-oriented programming? Well, it is an exploitation technique that allows us to bypass several mitigations. For example, ASLR, executable space protections, and also code signing. And that is because when we are using ROP to exploit a given binary, we are executing instructions that are already present in the binary itself. And in case the NX bit is enabled, also known as DEP in Windows systems, data execution prevention, which means that we cannot execute code from the stack or heap, using ROP, we will be able to achieve the behavior we desire using code already present in the binary, in the text segment of the binary, for example, which is executable by default. And in the case of ASLR, which randomizes addresses from the stack, heap, or dynamically linked binaries, we will be able to bypass it because we are hijacking the execution flow back to the binary itself. In case the binary hasn't been compiled with the PIC protection, that is position-independent code. In other words, if it isn't a position-independent executable, ASLR has no effect at all in the memory segments, in the memory sections corresponding to the binary itself, so we are automatically bypassing it, given that addresses will remain the same between executions. All of this will allow us to concatenate ROP gadgets in order to build our ROP chain and provide it as payload to our vulnerable binary. Now, what is a ROP gadget and a ROP chain? As it is stated in the Wikipedia, using this technique, an attacker gains control of the call stack to hijack the program control flow and then executes carefully chosen machine instruction sequences that are already present in the machine's memory, called gadgets. Each gadget typically ends in a return instruction, existing in the program or a shared library. So simply put, a ROP gadget is basically any instruction sequence that ends with a read instruction, with a return instruction. In order to better understand it, let me open with Cutter the binary we will be later exploiting, and let us see if we can visualize actual gadgets. Let us take a look at the main function, and here, right at the end, we can see there is a read instruction. This read instruction per se could be a gadget. If we instead take, for example, the pop RBP and the read instruction, these two instructions could be another gadget. If we instead take the address of the move EAX0 instruction and we take all of these three instructions, that could be another gadget, and so forth. And when we are chaining all these gadgets together, we are creating a ROP chain. How are these gadgets chained together? We will later see it and you will understand. Before proceeding, let us make sure we all understand what the read instruction actually does, because that's the key component of the return-oriented programming attack, hence its name, return-oriented programming. We have to make sure we understand what happens in memory in the stack when the read instruction is executed. And that's something that I've already discussed in a previous video. That's what the read instruction is equivalent to. Please make sure you understand that read instruction isn't internally performing a pop and a jump. We are just depicting, replicating its behavior in order for us to better understand what is happening, we are using alternative instructions just to mimic ret's behavior. The ret instruction is just that, a ret instruction. Now keep in mind that there are also some side effects. For example, this pop instruction will increment our ESP or RSP register, and it will place whatever the RSP register points to into the ECX register. And then jump will basically move our instruction pointer, our EIP or RIP, to whatever is contained in this ECX register. Okay, that's nice. So to sum up, the ret instruction basically pops the value that is pointed to by the stack pointer and places it into the instruction pointer. And of course, when you pop a value, the stack pointer gets incremented one memory cell. That is 4 bytes in a 32-bit architecture or 8 bytes in a 64-bit architecture. But before continuing, let us draw things, because it always helps us to better understand whatever we're trying to learn. Let's consider the following scenario I have drawn here. Let us take this stack, and when we are performing a ROP attack, the most important registers that we should care about are the RSP or ESP, that is the stack pointer. It always points or should point to the top of the stack, and also the RIP or EIP, and that is the instruction pointer. It points or should point to the next instruction to execute. Of course, these are not the only registers we do care about, because depending on the attack we have to perform, we may have to deal with any other register like RDI, RDX, RCX, whatever. Imagine for a moment that we are about to execute this ret instruction we have right here. So the expected behavior is that RSP points right to the top of the stack, because we have already executed the function's epilogue, so this RBP isn't here anymore. And now, when the ret instruction gets executed, the value that is contained in this memory cell, this address, will be placed into RIP. In other words, right when the ret instruction places the value that RSP points to in the RIP register, RIP now points to somewhere else, we don't really care. And of course, the RSP register gets incremented. Remember that it isn't a pop operation, it's just that the ret instruction affects the RSP register. So this is the normal behavior when a given function is about to exit. That's what happens when the function's epilogue gets executed. So let us now consider the following scenario. Suppose we are executing a vulnerable binary that we can abuse, we can exploit by using ROP, and say that we achieve the vulnerable function that allows us to perform a buffer overflow. Let's say we are writing right from this memory address. So since there is a buffer overflow, we are actually able to overwrite all these memory addresses. We are smashing the stack, we don't really care about the values we place there, it's just padding. And then when we reach the legit return address, as always, we want to hijack the execution flow. So we overwrite, for example, this return address with the value of a given ROP gadget we have carefully chosen. Let's say, for example, just for the sake of the example, we want the execution to jump right here to perform the pop RBP we have right here. So we place the E6 address. That is, we just keep writing. Remember that writing into memory happens from lower addresses toward higher ones. And when we reach the memory cell corresponding to the return address, we just write E6. Then we keep writing because we want, say for example, to place an arbitrary value in the RBP register. Let's say I want to place a 0 in the RBP register. And then I want the execution to return once again to the main function, for example. So I want it to return to the 97 address. So I'm writing a 97 in the next memory cell. Let us now see how all these values work together when we are performing the ROP attack and understand what's happening in the registers, especially in RSP and RIP. Suppose that we are right at this moment during the execution. We are about to execute the ret instruction. We have already overflown, smashed the stack. So of course we expect the RSP register to be pointing to the memory cell corresponding to the return address, which we have overwritten with our desired value. In this case, when the read instruction gets executed, what will happen is that E6, which is the address of the next instruction to execute, will be placed into RIP. So the RIP will now point to our gadget, which is around here. And of course, remember that the read instruction has effect on the RSP register, and that is, it just increments it. So now the execution, the RIP, is right here, where our gadget is at the E6 address, because that's what happened when the read instruction got executed. So now the pop RBP is about to be executed. Remember that stack operations, pop, push, and so forth, all of them, they do rely on the RSP register. That's its main purpose. That's why it is called the stack pointer. So when we perform a pop operation, what will happen is that it will take whatever value the RSP register points to and will place it in the register we specify. In this case, it is RBP. Since we are popping a value, of course, the RSP register gets incremented, so it will now point here, and the value it was just pointing to will be placed in the RBP register. Of course, since we executed an instruction, the RIP register will point to the next one, which is just this red we have right here. Now the execution must continue, and what will happen is, once again, that we are about to execute a read instruction. In other words, the value pointed to by RSP gets placed into the RIP register, so RIP will now be pointing to the beginning of main, and that happens to be somewhere around here. Since we executed the read instruction, also the RSP register gets incremented, so it will be pointing to the next memory cell. And this is how all these concepts work together, and we managed to overwrite, or rather to place in the RBP register the 0 value, and that's what we wanted. And we also managed to hijack the execution flow, and we executed main once again. All these things that I have drawn here are the ROP chain we executed. Of course, in this case, it contains only one actual ROP gadget, but we could concatenate as many ROP gadgets as we desire until we execute the behavior we desire, as long as we have, of course, enough space to write, because we depend on how many bytes are actually being read. And after all this theory, let us put it into practice and exploit the binary I have mentioned from ROPEmporium, which is called split. Since I'm using the latest version of Cutter, they have fixed the bugs, and now I am able to check the protections this binary has been compiled with right from Cutter. And we can see that it is a 64 bits executable. That means that parameters to functions are passed via registers, not via the stack, which is the case in 32-bit architectures. We can see it has no canaries. It has been compiled with the no executable bit. That means that we cannot execute code from the stack or heap. We cannot execute the shellcode. And it isn't a position independent code, so addresses from the binary itself will remain the same between executions. And we don't really care about relocation read-only in this case. So let us take a look at the code itself. Well, actually before that, let us first execute the binary and see what it does at a first glance. So it prints information about the binary itself, and it asks for input. Thank you, exiting. Okay, let us check if the binary is somehow vulnerable to buffer overflows. Let me provide a pretty long inputs. We got a segmentation fault, and that is because we somehow managed to overwrite the return address. Okay, so the binary is vulnerable to a buffer overflow attack somewhere at some place. Let us just keep taking a look at the binary itself. By inspecting the functions the binary has declared, we can see at a first glance there is already a punme function and another useful function that of course seem to be of our interest. In the main function, however, we can see the execution is pretty standard. We got printed the information, and then it calls the punme function. Here in the punme function there is a call to memset to puts that prints the contriving reason to ask for data, whatever, and then there is a call to read. that actually reads from the 0 file descriptor, and the 0 file descriptor corresponds to the standard input. And we can see it saves the data in the RSI buffer, which RSI is the address of buffer, that is RBP-20, and the function reads up to 60 in hexadecimal or 96 in decimal bytes. So here is where the vulnerability lies. The function read is writing up to 96 bytes in a 32 bytes long buffer. So given this vulnerable scenario here, we are actually able to overwrite the return address of the punme function, and let us see where we want to hijack the execution flow. What do we actually want to execute? Usually when we deal with this kind of vulnerable binaries, the objective is to spawn a shell either in the remote or local machine. However, in this case, given that I have downloaded the binary from ROPEmporium, the objective is to read the contents of this flag.txt file that we get when we download the challenge per se. So let us take a look at this useful function we see right here. It's just a function that performs a call to system executing bin ls. Let us take a look at this value right here in the hexdump view, because there isn't a function that we can inspect. And we can see that it indeed corresponds to /bin/ls string. So that's what system will execute. Okay, we have a system call right here that we could abuse if we somehow manage to provide as first parameter any given command that would allow us to actually inspect the contents of flag.txt. We know, of course, beforehand that we can jump right to this address right here because the binary isn't a position independent executable, so these addresses won't change. So let us copy this address here and start preparing our exploit. As always, I'm using puntools to create the exploit, and I'm setting the environment variable context with the binary split that we are actually trying to exploit. And I have just noted the address of the system call, and I am using pack for 64 bits because we want this value to be 8 bytes long and little endian. And just as a note to myself, I have also specified that read writes from RBP-20 up to 96 bytes. Okay, so now back to our binary. We have seen that we want to somehow modify the parameter that the system function receives, and that is the EDI or RDI register. And why is it this particular register? Well, that is because of the calling convention. For 64 bits in Linux systems, which is where we are, right here, the parameters to functions, the arguments are passed via the following registers in order. Since system receives just a single parameter, the RDI register is used. The second parameter, which is not the case of system, would have been RSI, RDX, RCX, and so forth. So we want to modify, we want to give RDI a given value, an arbitrary value. And what is that? We want it to be the address of a string that isn't just ls. It could be any other string that allows us to inspect the contents of flag.txt. So first, let us take a look at what strings are there present in the binary. In the binary we are exploiting. And by taking a look, we see that right here we have a carefully placed string that is cat flag.txt. While this isn't usually the case, given that this is an easy challenge for all of us to learn ROP exploitation, it is pretty handy right now. So let us copy this address and paste it in our exploit, because somehow at some point during the execution we will have to reference this address right here that actually prints the contents of flag.txt. And now we have to think, how can we actually change the value of EDI or RDI register? And here is where ROP gadgets come into play. We have to find all the gadgets present in this binary, and maybe if we are lucky enough, we get a gadget that modifies the EDI or RDI register. Now the question is, how can we find specific gadgets in a given binary or shared library or whatever? Well, there are many tools that help us with such a task. For example, Cutter per se has a search function that allows us to look for specific ROP gadgets. Or for example, if you prefer any other tools, you can use ROP gadget wrapper, a module from puntools, which is the ROP module that allows you to look for any specific gadget or ROP chain you want, and also radar2 allows us to look for gadgets using the /r function. This time, however, I will be using ROP gadget. So in order to use it, I have previously installed the tool, of course, and I have to specify the binary I wanted to analyze, the depth of the ROP search engine, which by default is 10, I like to use 12, and then I'm simply redirecting the output to a given file. So now let us execute it and take a look at the gadgets it finds. Remember that we were looking for a gadget that modifies the RDI register or the EDI register. And here we have a gadget that pops a given value into the RDI register and then returns. These are the gadgets that are most useful because there is just a single pop operation and then it returns. There are no collateral effects or side effects. For example, imagine you want to use a pop RBX register and this is the only gadget you have. You would have to provide values, of course, the desired one, the arbitrary value for the RBX register, but then values for RBP, R12, 13, and so forth. So you have to, of course, count with every single pop operation the gadget is performing. In this case, this is the address that we are interested in because that's the gadget that we will be using. So now that I found and specified the addresses that I really care about, let us define the process we are about to execute and let us receive until, and let me relaunch the binary once again. So when it asks for input, we have this character right here. So we will be receiving until we find this character, and then we have to provide our payload. The payload in this case is very simple. Given that read writes from RBP minus 20 in hexadecimal, we have to provide that many padding to reach RBP, and then 8 more bytes to overwrite RBP itself and reach the saved return address. And then we are hijacking the execution flow with the pop RDI address because we want the execution to jump to this gadget right here. And of course, we want to overwrite the RDI register with the value of our cat flag txt string. And then we will, of course, execute system. We will send this payload to the binary using just send, and then we will receive all, and the execution will finish. With this payload we have just defined, we will achieve the following behavior. We will smash the stack just like so. With these two first payloads we have defined here, which are just padding, we will overwrite up to and including the RBP. We will smash it. Then in the legit return address, we will overwrite the address of the pop RDI gadget. We want the RDI register to be fulfilled with the address of the cat flag txt string, which is the next value we have right here. And then, of course, we want the execution to jump right where this system function, the system call is. And that's why we are providing the address of the system call. In other words, right when the punme function, which is the vulnerable one, is about to exit, we will be in the following scenario. So the RSP will be pointing to the address of the pop RDI register. The red instruction, this one we have here, will get executed. So the RIP will be pointing to the pop RDI, and RSP register will get incremented once again. So it will point to this memory cell right here, which contains the address of the cat flag string. When the pop RDI register is executed, it will, of course, place the address of the cat flag in the RDI register, and then once again the RSP register is incremented, so it will point to the address of the system. And right after we have the pop RDI register, since we are performing a ROP attack, this is a ROP gadget, we have a read instruction. So when the read instruction of the pop RDI read gadget is executed, it will take the value that RSP points to, and that is the address of system. It will place it into the RIP register, and the RSP register is incremented once again, but we don't really care about this memory cell anymore. Now, the call to system will be performed and it will execute the command contained in the RDI register, which is the first parameter. Given that system takes only one parameter, it will execute the cat flag txt command. And after all this talking, let us actually try it. In order to execute the exploit, I will just simply use Python 3. We are receiving all the data, but what happens is that I am not printing it. So of course, let me print it. Let's see now. And here we have it. This is our flag. We can actually check it by printing the contents of flag txt, but we managed to do what we first intended, and that is exploiting the actual vulnerable binary to read the contents of a file. Now the question is, what happens when the binary we are trying to exploit does not contain the gadgets we need? We would have to perform a more advanced version of a ROP attack, looking for gadgets in other places like shared libraries. A very known attack that does just that is return to libc, also known as read to libc. And that's exactly what we will see in the next video. In this video, we have seen what return-oriented programming is, also known as ROP, what happens in memory with the RSP and EIP registers when we are executing a ROP chain that comprises ROP gadgets. I hope you found the video useful, and if there is anything you want to say, leave a comment below. Remember, exploit code, not people. See you in the next one. Until then, GG.